First I'd like to thank to the committee of this conference, and the organization, and also Professor Lev and Judy for being kind and having solved all my problems for coming here. Thank you very much. And so my name is Andrey Chaves, and this work is a result of a collaboration between me and Professor Judy Aquino Farias. We are from Universidade Federal do Ceará in Brazil, and also with Professor Peters from Antwerpen and Bartolomé Zafran from Poland. So maybe most of you must know about these people who had been able to grow this kind of structure, which is made of semiconductors, and it is like a quantum ring with some leads. And also you see that some people have already done some calculations with considering a thin line as a ring and these leads here. You see that there are also other kinds of topology or geometry. And people consider the case of a Gaussian wave packet traveling through the system and calculated the transmission here. And they see the Aharonov-Bohm oscillations as a function of the flux treating the ring. What we have done is to consider the same system, but with a finite width, like this, but in order to try to see what happens in this kind of experiment, for instance. So the main difference is now that as we have a finite width here, we have kind of different bands here. When we were working only with a line, the wave packet was locked in one subband. But now, as we have a quantum well, the wave packet, if it has energy enough, it can be scattered to other subbands. So I'd like to show some movies of this time propagation of the wave function. Let me see. This one, for instance, is an electron with an energy which is in the first subband, like in the ground state of the quantum well. Let me see if it's going to work. So you can see that the wave packet passes through the ring, and you see that it starts in the first subband here, and in the other side you see that it has only one peak, so it's still in the first subband. Here it's still in the first subband also. You have only one peak in this part. But let us see what happens if I start with a higher energy, like 180. This is energy enough to go to the second subband. So here you see that here you have a second subband state because you have two peaks. But here you have only one peak, so you are still in the first subband. But if you put a magnetic field, something strange happens. The second subband state is allowed to get out of the ring. And that's what I'm going to show. The phase due to the magnetic field makes the wave function to be able to get out in a second subband instead of the first one. So if you want more information, you can see in our paper in Physical Review B. Let me see if I can get here in Physical Review B is there reference to, or go to my poster. So thank you very much.